Hello, welcome everyone. We will be talking about Nernst and Rest potential in this set of slides. This forms part 2 of Software Lab 0. This is part 2 of Software Lab 0. So we start with the question, what is the power source for a neuron? You have close to 86 billion neurons in your brain. Typical human brain has that many neurons. What do you think is the power source for those neurons? Where do those neurons derive the power to do all that they do? Think about that a little bit and see if you can jot down a few thoughts. Just jot it down in your notebook, and you'll need a notebook as you go through this because I'll ask you in between to jot down thoughts. So please keep that ready. Go to slide 2. So these are the questions you will need to answer on part 2 of software assignment 0. Okay, and then so you will understand these questions after we are done with the lecture, just so you know where it is. Moving to slide 3, we talked about capacitors in a previous lecture. Every cell in your body carries a potential difference across the membrane, the cell membrane, that acts as a battery. Think about that a little bit. Every cell in your body carries a potential difference across the cell membrane that acts as a battery. So I have two questions. How can this be a battery? Think about that a little bit and connect it to the circuit's battery that you're familiar with. Again, jot down your thoughts. And the second question is, why do you need for a battery, what do you need for a battery to do something useful? So the second question is, what do you need for a battery to do something useful? These are pretty generic questions which may be difficult for you to think about, but I do want you to think about it. This is how we think of biology as an engineering system. By engineering system, I just mean how does it work as a physics system. We are looking, our quest in this course is how does this work using fundamental laws. So think about this and jot down your thoughts. Okay. How is this battery created? We need to know that. So moving to slide 4, this is the typical structure of a cell. I don't know if you can zoom in, on the cell membrane and make sure that you understand that it's formed by a lipid bilayer. Right? You can see the lipid bilayer and try to sketch it in your notebook, that lipid bilayer, which we have done in class. So across the cell membrane, there will be a concentration gradient, meaning you have, in this particular case, you have a lot more potassium ions inside than outside. You have more potassium, the concentration of potassium ions is larger inside than outside. Okay. So we will assume a concentration gradient has been set up. We'll come back to this question later as to how did this happen? How did this concentration gradient, meaning larger concentration of potassium ions inside and compared to outside, how did this get set up? Who did this? We'll come to that question later. Then let's consider the concept of an equilibrium potential. So if you go in and record the potential difference across the cell membrane, you will find a number like minus 90 millivolts, meaning the inside is more negative compared to the outside. And the potential difference is minus 90 millivolts. Okay. So as you look at this and make sure you understand this, this is assuming only one ion can diffuse through the cell membrane. If you assume only one ion could diffuse through the cell membrane, this is what you get. And that's what the text on the slide says. If membrane permeable only to potassium, it would diffuse until its equilibrium potential. That's denoted by EK. K stands for potassium there. That is reached. K plus is attracted inside by trapped anions but also driven out by its gradient. At equilibrium, electrical and diffusion forces are equal and opposite. And that's what we will be talking about in the rest of the slides. That statement, at equilibrium, electrical and diffusion forces are equal and opposite. So don't worry about that. We'll be talking about that next. What you have to get from the slide is the structure of this cellular membrane, and then the fact that if you record the potential difference between inside and outside, you typically will get a minus 90 millivolts type thing. There is a flaw in this picture. In this schematic, something is wrong, something is missing. I'd like you to note in your notebook as what is the error or what is the intentional flaw in this picture. We'll come back to that later. And if you don't see it, just make sure you ask me in class what is the flaw in this picture. Let's move on to slide 5. So here we consider the question, how might have Nernst come up with this celebrated equation which connects this, provides this equilibrium potential. The equilibrium potential we talked about on the previous slide, where the diffusion forces balance the electrostatic forces. How might we come up with this? Again, jot down your thoughts. What do you think he did to come up with it? So we will consider 2 experiments to determine the Nernst potential for potassium. That is the experiment on the left side, on this side, and the other one to determine the Nernst potential for sodium, which is this set of experiment on the right side. Okay. Since the procedure is the same for both, we will actually just focus on the left side. Assume a tank that can be divided into 2 halves using a semi-permeable membrane. A semi-permeable membrane is a membrane that permits only selected ions to permeate or move through. Permeate means move through. Semi-permeable means it allows only selected ions. In this case, in the case of the figure on the left, it will permit potassium ions to move and nothing else. So imagine you can buy a membrane that will only permit potassium ions to move. Do you know where you can buy such a membrane? There are a lot of biotech companies in St. Louis and Kansas City. You could call one of them and they can provide you with a membrane that will be permeable only to selective ions. You could say, I want a membrane that's permeable to sodium, and they will ship it to you. Okay. Now consider the panels on the left side. So the experiment starts with the top panel A. That's when you start it. And then as you go down to B, C, D, and E, time progresses as you go down. So you can imagine a time axis pointed downwards. Time increases as you go down. So what happens starting at time t equals 0? So what will happen is K plus will start moving from the right side to the left side through the semi-permeable membrane, as shown in schematic panel B. As you know, we always ask why till we get to the fundamental laws, and that's how we design this course. This course is meant to, meant to get to the question of what are the fundamental laws that govern the phenomenon you see in neurons, and how do you write it in terms of equations. That's computational modeling, or computational thinking, or quantitative reasoning, whatever you like to call it. So in this case, the movement of ions, K plus ions, from the right side to the left side follows the law of diffusion, which states that molecules of any type, charge or not, any type of molecules, will move from a region of higher concentration to a region of lower concentration. And that is the law of diffusion. What happens as this diffusion continues? The K plus ions that diffused left that chloride Cl minus ion, those buddies, behind, right, on the right side. So the chloride ions will continue to accumulate on the membrane wall as shown in panels B, C, D, and E on the left side. On the left side of this, pictures, but in the right compartment, on the right side of the panels, the chloride ions will continue to accumulate. Right? This then begins to create an electric field that opposes the flow of potassium ions from the right to the left. You can pause this video and try to understand this point. Again, there is a set of the diffusion force which tries to move ions from the right to the left because there is a larger concentration of potassium this side and there is a lower concentration this side. So it will move ions from the right to the left. While the electrostatic force, which is due to this positive charges on this side, negative charges on that side, the chloride ions, that'll try to push this way. So this force is initially much larger, but as ions begin diffusing to the left, you begin building charges on this left side, and then the electrostatic force gets stronger and stronger. In this panel, you'll see schematically, we've shown that the diffusion forces, if the length of the arrow represents its magnitude, the diffusion forces sort of balance the electrostatic forces. From then on, if one molecule, K plus molecule, moves this way due to diffusion, and another K plus molecule will move this way. So you come to a dynamic equilibrium. So as you go down these panels on the left, you will see that the electric field keeps increasing. This goes on till an equilibrium occurs between the diffusion force trying to move K plus ions from the right to the left and the electromotive force that tries to move K plus ions from the left to the right. Okay. So we now have two opposing forces which need to come to an equilibrium. And Nernst used logic such as this to actually come up with the Nernst equation. That is the logic Nernst used to come up with the Nernst equation, as we have explained in class. The next step then would be to write down the law of diffusion in mathematical form, and then write down the law of diffusion, a law electrostatic force, the force due to electrostatic field, in mathematical form, and equate them. Nernst did that. So this would be a force on, let us say, one K plus ion. What is the diffusion force and what is the electrostatic force? Put them to write an equation and say, put them on either side. And he did that. Nernst did that. And then he simplified the equation, moved terms around, and arrived at voltage V Nernst equal to. And that's how we get the celebrated Nernst equation. So we will pause here before we go to the next. So try to think about this. We just basically pictorially represent all this now. So imagine that cell membrane, which is semi-permeable. And then you have diffusion gradient. In this case, the potassium is at a higher concentration on the left side. It moves from cytoplasm. It's on the left. So diffusion gradient exerts a force to the right. And then you have electrical gradient, which then comes to balance it. So this is a pictorial representation of how Nernst would have grappled with this problem. At what voltage will the diffusion forces balance the electrical forces? Let's move on to slide 7. This is a summary of what we just talked about. So I'd like you to maybe pause this video at this point and then go over this and make sure you understand it. Okay. More summary and explanation on the next slide, slide 8. So Nernst solved this problem way back in 1905. And he did it as a chemist. He was not a neuroscientist. Neuroscience was probably at its infancy, if at all. This was done for a chemistry problem, not for a neuroscience problem. So you know these laws apply in all domains, right? So here's a potential question in a quiz or a test. Devise an experiment and explain with sketches and text how will you determine the Nernst potential for sodium. So if you're asked this question, here's what you're supposed to do. This is again a summary of what we have done in the previous slide. So I'll suggest you take time to understand all this. I won't go over the slide. So this is a potential question you may get asked, and we tell you what you should do, how you should answer this. Okay. Go to the next slide, slide 10. This gives you the actual Nernst equation, and we would like you to really understand this and be able to write this. So it says V equilibrium or Nernst potential is equal to RT divided by ZF multiplied by natural log. Ln stands for natural log as opposed to log, which stands for log to the base 10 or so. Ln is a natural log of concentration outside divided by concentration inside. And this basically came from the equation where electrical force terms were on the left and diffusion force terms were on the right. And I'd like you to go over all of the details in the slide and make sure you understand it. We will want you to remember just this equation. I think it's a very useful equation. All biologists remember it, so it's worthwhile remembering this equation. Okay. Move on to the next slide, slide 11. We show you typical concentrations in neurons. This is typical. It varies from cell to cell, but typically sodium will be concentration, extracellular concentration of 145 millimolar is typical for sodium. Intracellular, it may be about 12 millimolar. Potassium has a higher concentration typically inside the cell than outside. Chloride has ion, which is negative, has a higher concentration outside than inside. Calcium has a huge concentration outside. The concentration difference is really huge in the case of calcium. And on the left, we show you the equations for Nernst potential for these ions, how you would do it. Put those concentration values into those equations, and then it'll give you the Nernst potential for that ion. Notice a key point to note here is that the Nernst potential depends on the concentration. It's not a fixed quantity. So for different cells in your own body, the Nernst concentrations will be different. For neurons in one part of your brain, the Nernst concentration for sodium may be 55 millivolt. At another part of the brain, it could be 52 millivolts. So they do differ, depend on the concentration. You have to know the intracellular and extracellular concentrations to determine the Nernst potential. Go to the next slide, slide 12. For a squid giant axon, here are some numbers. And on the next slide, we'll show you how to calculate some more details. These are all details. And then finally, I think there are calculators available on the internet. Please try these out. It gives you more details about Nernst and Rest potentials. So we will stop here for the moment and then come back to the material starting slide 15 in a different video. So that's all for now. We'll get back to this very soon.